Okay, so that's according to standard model, and basically you have the quarks and the leptons. They are the basic constituents of matter. Then theoretically you have understood all the standard model, how to calculate everything, but you have to do experiment also, and for the experimentation you have to perform whatever standard model says or whatever particle physics says. You have to explain it and understand it through the particle through the experiments. Okay, that means you have to perform the experiment which can give you the interaction among the particle, whether it's a electromagnetic interaction or it's a strong interaction or a weak interaction. So that means you have to perform the experiment for all the three types of interactions, and then whatever are the possible interaction among various particles, you have to try to understand through experimentally. Okay, so long days back earlier, how you perform the experiment, there was no accelerator, so mostly you had a cosmic ray experiment, and cosmic ray experiment you can get the beam. Okay, there are two components to study experimentally something. One is in particle physics, one is the accelerator, which will provide you the beam, and another would be your detector. After the interaction, you will produce particles, or whatever is the result of the interaction, you will detect that. Detect that one, and that is your detector. So that means you have two components. One is the accelerator, which provides the beam. Another is the detector. Okay. So for the old days, you had no accelerator kind of thing, so you had only cosmic ray. So that means in the cosmic ray, you will get the particles, and particles would be accelerated. They will have accelerated beam kind of thing, and then you put the detector, and in the interaction you will see all the. So whatever were the discoveries old days, that means how many particles are coming from in your atmosphere, and then whether you are getting protons, you are getting electrons, where from they are coming. So all those kinds of interactions you had done through the cosmic rays, but detectors were mainly nuclear emulsion. Okay, so nuclear emulsion is nothing but your photographic film. So the particle passes through, it ionizes, and then you develop that like normal picture, and then you will get 1 point or a few points, and those points you will try to make as a trajectory, and then you will see, okay, this is the kind of direction of the particle. That means after the interaction, you will see several particles are coming, and you get the trajectory of those particles. If you place that in magnetic field, then these charged particles will have a curvature. So if you have a curvature, you can measure the momentum. So those were the days when you were having the nuclear emulsion as a detector, and beam was the cosmic ray. Then came a spark chamber. A spark chamber is almost similar to the bubble chamber. I'll come to that one. So in the spark chamber, you have two electrodes, and it's a gas field. Okay, very high electric field applied, and then when particles are passing through, it will produce the sparks. And then you can take the picture of those sparks, and then sparks direction will give the trajectory of the particle. Okay, so those were days about this one. Then came the bubble chamber. Okay, so bubble chamber made several discoveries. What is bubble chamber? So bubble chamber is nothing but a chamber. You can consider like a cylinder. Okay. Okay. So it has a gas field, and what is gas? Okay, gas you will consider which can produce the tracks, as well as which can become as a target. Okay, so if you want to have interaction of any particle with proton, that means you can take hydrogen as a liquid, gas, cool it down, and then it becomes your hydrogen gas in the liquid form. Okay, you can take deuterium also. So that means now your interaction will occur rather than proton with the deuterium. You can take neon gas also. Any kind of inner gas that can be used as in this one, which is the gas form. Okay, in the bubble chamber. So earlier days you had deuterium, neon, okay, and even let's say propane. So these were the several gases were used in the bubble chamber. Okay. So now what is the working principle? Working principle is you take the hydrogen gas, apply very high pressure, okay, and then cool it to very low temperature, almost like minus 20 degrees centigrade. Okay, so that will becomes in the liquid form, and so in this liquid form, this will be your liquid. Your chamber is filled with the liquid. Okay, so that is your detector. Okay, now what are the particles? Okay, in this particular case, what you are trying to do in the MSc lab, you have a beam of you have a beam of antiproton. Okay, so these were the days when you had very, very low energy accelerators, and this accelerator could provide the beam of antiproton with 760 MeV. Okay, very fair. Tevatron, that was the proton which had something like 1000 GeV, you can imagine. So almost you can say MeV. So you can say 1 million times more energy could be acquired as back as 1995, and this was the time when you were trying to perform the experiment with antiproton with 760 MeV only. Okay, so how do you get the beam of 760 MeV? Can be got from the your linear accelerator that time, or cyclotron, superconducting cyclotron. There are various types of accelerators which can produce the beam of the low energy one. So let us concentrate only on the experiment which you are doing in the MSc lab. We'll consider later on that. So in this experiment you have beam of antiproton with 760 MeV. Now question comes, where from this antiproton is coming? In the Viva, most of the students say they are coming from cosmic ray. So most of the students do not understand where from the antiproton are coming. So first question comes, first you produce the particle, only then you can accelerate it. If you don't have particle, you cannot accelerate. And antiproton cannot be available in the nature. So that means you have to first create this antiparticle, antiproton, only then you can accelerate it. Okay? So firstly, how to create this antiproton? This is not naturally available. So for that one, you have first accelerator proton synchrotron. So with proton synchrotron, you accelerate the protons with 200 GeV energy, or very large energy. Okay? So in this case, you will take the proton synchrotron, accelerate it, the protons, and bunch of beam of the antiproton proton is coming. This is only proton. Then put here a beryllium target. Okay. So beryllium target, and with energy is 200 GeV. So you have to always remember, whenever you have energy, so that means this will work like a wave with a wavelength of h over p, lambda or h cross over p. So that means your p would be your momenta, and so approximately 200 GeV is your energy. So you can get. So wavelength is very, very small. So when you say wavelength is very small, that means it has a probability to interact to a size of only a nucleon size. Okay? If energy is 760 MeV, then its wavelength would be large, almost comparable with the size of your nucleus. Okay? So in this case, target would work as a nucleus, as a one object. If energy is more, wavelength is less, that means target would work, whole nucleus would work like individual nucleons. So you will be able to see individual nucleons separately if energy is large. Okay? So that is the idea to go with the higher and higher energy. If you go to tevatron, so energy in tera electron volt, wavelength is less than the size of the nucleon. So that means now you can go deep inside the particle also, proton, nucleon also, and that is at the quark level. So that means now you have a proton, target is your beryllium, beam is proton, so that means you will have proton beryllium interaction. Okay? And as just discussed, beryllium would not work like a whole atom. It won't work like your system of atoms, but it will work like an individual nucleon. Okay? So that means nucleus, which consists of large number of protons, neutrons. This proton is coming with a very small, with momenta of 200 GeV. Okay? Wavelength is very small. So that means it will observe individual nucleons. Okay? So it would be almost like a interaction with individual nucleons. So proton, rather than interaction with a proton and nucleus, you will have interaction between proton and proton. Okay? So now energy is 200 GeV. So that means what is the rest mass of one pion? 137 MeV. So that means you can create thousands of pions. Okay? So now, so what kind of interaction it is? Proton interacting with a proton. Either you can have electromagnetic interaction, that means charge-charge interaction. That is just simply your Coulombic interaction. So that means proton get scattered. So this is this is almost like a elastic scattering. So but this is your charge-charge interaction. So this is your electromagnetic interaction. One possibility is this one. Another possibility is proton interacts with a proton. That is your strong interaction. So this one is your electromagnetic interaction. Then you can have this strong interaction. So in this strong interaction, energy is large. So then you can create large number of particles. And what those particles would be? Those particles would be exactly whatever is the conservation law for the strong interaction. Okay? So that means it would be producing your large number of, you have initially two baryons. So that means outer you will have either two protons, or you can have one proton, one neutron. You can have a strange particle, all the possible combinations, whatever you find in the strong interaction, that you will apply over here. Okay? So nature will apply, and then you will create the large number of particles. There is a strange particle possibility, k plus k minus also, and again strangeness would be conserved. So now what is our aim? Our aim is to get proton, antiproton beam. Okay? So how to get that one? There is a possibility in this one that you get an antiproton also. So you will have this way, plus large number of pions. Okay? So first probability is that in this case, in the strong interaction, you will have 90% of the particles are pions because they are the lowest mass particle. Few percent, 4 to 5% are kaons. Less than 1% are protons or nucleons, you can say. But conservation law has to be there, whether it's a strangeness or it's your isospin or it's a baryon number conservation or your, so lepton cannot be produced because lepton, this is a strong interaction, leptons are not produced in this interaction. So these are the strongly interacting particle. You can have lambda particle, which is a strange particle. You can have K, you can have baryon, any kind of combination. So there is a very small probability that you will have antiproton also. Okay? So for antiproton, you will have 4 baryons. Okay? One antiproton, proton, or you can have proton, neutron. So that way you will be getting very small percentage of antiproton. So these particles would be large in number, so you can say almost like proton is coming, interacting with the target, and then you have large number of particles. There could be neutral also, it's not necessary that you will have charge. So among these ones, as mentioned, 95% are pions, 4% something like are the exchange, then less than 1% would be your baryons like proton, antiproton, etc., etc., etc. So in this one, almost in millions of interactions, there is a probability that you will have one antiproton. Okay? So you separate out that antiproton by mass separator. Mass separator is nothing but your magnet. And then if you have antiproton, this antiproton you separate it out. So that becomes your beam for this one. And then you have accumulator. Accumulator means in the magnets you keep on revolving them and then keep, so they have a lifetime also because they will interact with the proton and may get annihilated. Okay? So you take the beam of separately. Now what is this energy of this antiproton? This energy of this antiproton would be, this is 400 GeV. It could be varying because energy is shared among a large number of particles. This could be 1 GeV, it could be 2 GeV, it could be 5 GeV, it could be a few hundred MeV, it doesn't matter. You take out all these antiprotons and send them again in the proton synchrotron. Okay? So these antiprotons with the varying energy are sent to this antiproton synchrotron, like this one, and then they are accelerated. And our aim is to have 760 MeV. Okay? Then tune the energy, magnet and electric field. Electric field, your electromagnetic waves, RF cavities. So you have two types of instrument for the proton synchrotron. One is magnet, like exactly if you go to cyclotron, you have a magnet, and then you have RF cavity. Magnet keeps the particle to revolve in the circular orbit, and electric RF cavity works to accelerate it. As soon as it comes, let us suppose you have RF cavity over here. As soon as particle comes over here, it gets a kick. If we had the voltage, RF cavity voltage, that means energy would gain by this one E times of charge on the particle multiplied by V. So that way its energy will increase from the, as soon as energy increase, you have the magnet and try to keep in the orbit again. So this way it is again moved over here and it comes back. So every time it passes through RF cavity is only at one place. As soon as it passes through the RF cavity, it gets accelerated. And that's how its particle gets keep on accelerating. So once it has acquired the 760 MeV, then you allow them to pass through the detector, okay, and allow it to have an interaction. So, so this one is your now beam of 760 MeV. So most of the students, they keep on telling that the antiprotons are coming from cosmic ray or they are coming from here, they don't know. So you have to first create antiproton, accelerate them, and then accelerate to the tune energy, and tune energy in your case is 760 MeV. Okay? So 760 that's how you acquire the energy of antiproton with 760 MeV. And now allow them to pass through the bubble chamber. Okay? So this one is your bubble chamber. So what is the working of the bubble chamber? As previously mentioned, it is filled with the liquid gas in the liquid form. Liquid form means cool it to very, very low temperature and very, very high pressure. Okay? So now you have pistons. Okay? As soon as beam enters, and beam is not just one particle, but here there are few particles because you want to see them. only 4 or 5 particles are entering here, not like Tevatron or not like LHC. In LHC you have the 10 raised to the power 12 protons which are entering in the detector. Here they are not so many. Here only 5 particles are entering because you want to see them, visualize them. Okay. So these antiprotons are coming, entering over here. And now target is filled with the hydrogen. Okay. So when they enter, it is in the liquid form. It is cooled to very high pressure. It will start ionizing the hydrogen gas. Okay. So along its trajectory, the ionization will take place. So hydrogen gas will get ionized. So in this process, now you release the pressure little bit. So when you release the pressure little bit, what will happen? It goes beyond the boiling point. Okay, because liquid is in the superheated state. Superheated state is nothing but if any kind of disturbance occurs, the energy would be available and that energy would be good enough to make the bubbles. Okay. So do you understand? This is called a superheated state. What is superheated state? Superheated state is when you release the pressure. Okay, you have applied very high temperature, very high pressure, and it's a very low temperature. So it's in the liquid form. Now if you reduce the pressure, what will happen? Your liquid will start boiling because it's in that condition. So you don't release the pressure too fast, as well as not too high, suddenly too much pressure, you don't release it. You release the pressure very little. Okay? So when you release the pressure very little, whole liquid is not boiling. Only wherever ions are there, that energy released in the ion formation, ion, electron and proton ions are produced, and that energy is good enough to make the bubble. Okay, so you will have a small bubble because at the place wherever ionization has taken place. Okay, so along its trajectory, ionization has taken place, and wherever ionization is taking place, that center becomes your center of condensation, where particular atom becomes your center of condensation. And energy available in the ionization, that would be good enough for the formation of bubble. And now if you keep the piston loose for a long time, then whole liquid is start getting the boil. Okay? So you immediately put pressure again, so the bubbles do not grow too much. So is it clear? So along its trajectory, if you have a neutral particle will not ionize. If it doesn't ionize, no ionization, no energy available, no condensation point. So condensation point is only the place where ionization has occurred. Okay? So along its trajectory, now you keep on getting the bubbles. So what you will be visualizing? You will be visualizing only the bubbles, nothing over there. Okay? So along the trajectory you have bubbles. And now you take the photograph. So you take the photograph from, with 4 different angles. Okay. So so that means each camera will give only 2D picture. Okay, X, Y. So if you have the 4 different cameras, so you can merge and make the 3D picture of these cameras by reconstruction. So what you have only the bubbles, and then the direction of the particle, wherever particle has gone, the trajectory of these bubbles will be, you can make the trajectory of the particle by joining the bubbles. Okay? So bubble tracks formation in bubble chamber follows this principle. So it is not a continuous line, but it are just bubbles along this wherever atom has gas ionized, and that will give the trajectory of the particle. Okay? So now if you put this in a magnetic field, So these particles will have the magnetic field will be there, and because of magnetic, if they have the charge, then you will have a curvature. So that means bubbles will be along the curvature line. So finally what you have got in the 2D picture, you have one antiproton is coming, that is entering in the bubble chamber. Let's take, if it's a 2D picture over here, you have bubbles formation like this one, and that is the trajectory. And what are these bubbles? They are the bubbles where the ionization has taken place. So you have a hydrogen bubble chamber, so that means you have protons and electrons. Okay? Ionization has taken place, so here is the condensation point of the proton or nucleus of the hydrogen. So that is your proton. So this process of ionization is electromagnetic interaction, because it's just a ionization. Ionization process is your electromagnetic interaction. So far no strong interaction has taken place. So these antiprotons are entering, and then you have this one. So now what you want to do? You are interested to find out how this antiproton interacts with a proton, because you have hydrogen atom over here. So one possibility is this ionization. So bubble formation is due to the ionization process, and that is your Coulombic interaction, and that is your electromagnetic interaction. Okay? If you want to study through this process electromagnetic interaction, you can do that. How? You find out how many bubbles are formed, what was the density of the liquid, then you can see what is the energy required for the ionization of your hydrogen, and that way you can keep on studying the electromagnetic interaction by this process. You are not interested in that one. Second process could be your antiproton is coming, it interacts with a proton, and then this is your target, this is at rest. Proton is coming with a 760 MeV. This you have to always remember. Rest mass of the hydrogen, rest mass of proton is 980 MeV. Okay. So that means it is this is the kinetic energy. So this antiproton comes, interacts with the target. Target is a proton, and proton is at rest. So that means it's a fixed target. Proton coming, interacting with the proton over here, and then this antiproton interacting with the proton. What is the possibility? Either it gets scattered, antiproton goes this side and this side. Rest mass of this proton was 0. Some of the momentum is given to this one. Maximum momentum was carried by 760 MeV. That goes on this direction. So this is the, now it will form the track. So how it will look like in the bubble chamber? It has bubbles, and then you get bubbles like this one. This is your antiproton track, and just little bit over here, that's your proton track. Why? Because proton is at rest, so some momentum is given to this proton, it gets scattered a little bit, so only few millimeter kind of distance you will be able to see, and that is your scattered proton. Okay? Whereas this proton, antiproton, which was carrying large amount of energy, that keeps on moving. Okay? So what type of interaction it is? Electromagnetic interaction, because charge-charge interaction, this is not a strong interaction. So you'll have a antiproton-proton interacting, this is this one. And this is kind of elastic scattering. Okay? So far nothing, no strong interaction has taken place. Ionization process was electromagnetic interaction. This is elastic scattering, that's also almost like electromagnetic interaction. No new particle created. This on ball is hitting the stationary ball and both are getting scattered. One with the large momenta, another won't be the smaller momenta. If the strong hard interaction takes place, that means in that case both the balls can have the same momenta. Okay. So this is your elastic scattering. So what you will count now in this case, you will look at the tracks. Okay. If you find one a small tiny track, another one is a very long track, then you will say this is your antiproton interacting with the proton, giving rise to antiproton with the proton, and that's your elastic scattering, and this you count as a two-prong. Okay? Generally this is not a two-prong because you have two tracks. One is this one, so this one is not generally counted as a two-prong. This is elastic scattering, two-prong, and this is called a stationary. And you can see it's a thick track and going to stop after traveling a smaller distance, and that length would be very, very small. Bubbles would be almost continuous. That will distinguish between this and energetic one. Length is small, in this case length is large, so you'll have antiproton interacting with the proton, giving antiproton-proton, that's your elastic scattering, that's your two-prong. Okay. Now there is another possibility, that's your strong interaction. Antiproton comes, interacts with the proton. Okay. Now for the conservation law, if you have shown, you will have this we have already done. Antiproton, proton. Can you create one antiproton, another antiproton? So you have two two initially stage particles, incoming and target. If both are this one, you cannot create this thing. Why? Because energy is 760 MeV. Rest mass for the one proton is 980 MeV. So you cannot create these two particles. Okay? So that means this is only this. So what is the possibility then? The possibility is this antiproton annihilates with a proton. Okay? So in that case you don't need to create your, because antiproton is antiparticle and target is your baryon number is +1 for P, baryon number for antiproton is -1, so baryon number conservation would result into 0. So outgoing is your pion. Okay? And that is your two-prong. So in this strong interaction, antiproton comes, that is a 760 MeV, interacting with the target, giving rise to two pions. If you want to have this proton, antiproton, that is also not possible. Okay? Because you can find out what is the center of mass energy. Okay? Center of mass energy, by calculating the center of mass energy, almost 50% energy is shared by this one, target, and 50 is this one, so almost 350 MeV of this one and 350 MeV of this one, almost like if you consider that one. So you cannot create this one. So possibility is only the annihilation. So antiproton interacting with the proton and it annihilates, it can give you the pi plus, pi minus, or n number of pi 0 because charge is not conserved. You can have pi plus, pi minus and pi 0 also. This is two-prong because outgoing particles are true. This is also two-prong outgoing particles are 2, but this would be a neutral, it won't give any track. Okay? So how it will look like in bubble chamber? You have antiproton, particle beam is coming. As soon as it enters in the chamber, you will find the bubbles, and it may travel to some distance. Then you will find some bubbles are going in this direction, some bubbles are going in this direction, and with a curvature. Okay? This one is your pi plus. From the charge, from the magnetic field, you can find out what is the direction of pi plus, what is the direction of minus. So you'll have 2 pions, charged one, and that you call it a 2-prong event. Okay? If you have a neutral one, neutral doesn't give any track because pi 0 doesn't have charge. If it doesn't have charge, it won't ionize. Ionization process is because of charge only, electromagnetic interaction. Pi 0 doesn't have charge. It keeps on moving, and let us suppose it goes in this direction. No track, nothing over there. Then after traveling some distance, it may materialize into 2 photons. Photons also do not have any charge. They will also leave no track. So what you will have, it can materialize into electron-positron pair. Okay? This can also materialize to electron pair. So what you will find, after traveling the distance, one may carry smaller momenta, another can carry large momenta, so one may escape the bubble chamber also. But if both of them materializes, then you will find one like this one, and another one is like this one. You must have seen these tracks. So what are these? These are the positron and electron tracks, because mass of the electron is very, very small, momenta is large, and because of that curvature is very, very large, and it becomes a spiral one. Okay? So you will have bubbles like this one. They are all bubbles, not a line, but if you take the photograph, they looks like line. So this corresponds to 1 photon, and there could be another in this direction, this one. So this is photon 1, this is your photon 2, and when you combine, you get their trajectory, you find out their angle, and try to make where from they are going. So they might be joining over here, and this joining could be your pi 0. So point of interaction of this line and this line will give the pi 0 over here, and this line will show that it is coming from this direction. Okay? So what you will get, only the 2 tracks. If you see downstream like this one, so that means they are photons. One electron is in this direction, positron in this direction, and then both of them are a spiral one, and they are joining at one point, and same way over here. So this is the trajectory of your photon. Okay? So nice picture you can see in the bubble chamber, how the trajectory of the photons looks like. Okay? Gamma looks like. So this is still, you count them, when you are performing the experiment, you still count them as a 2-prong. Okay? You don't count a neutral one, because it is difficult for you to trace back, and one might go miss also. So trace back to over here and find out what is the pi 0. So you have only charged one which are coming from the vertex, and this is called your vertex one. So proton was here. So this proton was participating in the ionization process. This proton was also participating in the ionization process. Only this proton is interacting, annihilating. So antiproton annihilating with the proton, giving you 2 pions and pi 0 also. Okay? So this is your 2-prong. Okay. Now there is another possibility that you can have proton, proton, antiproton, proton giving rise to 2 pi plus and 2 pi minus. Okay, so here it will look like bubbles, and then you will see one track kind of thing, this direction, and this is your 4 prong, and you are considering only charge 1. You can have neutral again here also, same way like 2 pi 0, 4 pi 0, because pion number conservation, there is no number restriction on the number, only energy is conserved kind of thing. Okay. So here you have 2 positive, that's pi plus, and 2 negative at the 2 pi minus, and then you will get the 4. So in this case, what is the probability between this and this one? That follows energy conservation law. Okay? Here energy is divided among 2, here energy is divided among 4. Okay? And it follows almost like a Gaussian kind of thing. So here is your 2 prong, 4 prong, 6 prong, and you can have 8 prong. Okay? If you look at the number of prongs, and on this side is the number of events. Okay. So another possibility that you can have antiproton interacting with the proton and giving you the 6. That is your 6 prong. So what you will be counting? First in the bubble chamber, what you will see some kind of interaction if it is occurring. You locate that interaction and then count the number of particles. Okay? If there are 4, you count them, write them in the 4 prong category, 2 prong category, or 6 prong category, or you can 8 prong category. Okay? More than 8 prongs is not possible, because if you look at the energy of incident beam is 760 MeV. To create 1 pion, you require 137 MeV energy. You can multiply how much energy is required to create, just create the particle, and then they are carrying certain momenta also. So energy momentum conservation, you have to apply. You find out what is the center of mass energy, and you cannot get more than 8 prongs. Even 8 prong is very, very rare. So if 8 prong is there, in that case all the 8 prongs would be very, very low momenta, because energy, rest mass energy is given to create the new particles, new pions, and then momenta of these 8 shared among all the 8 particles. Okay? So you can have 8 prongs. Another picture you might have seen, something like this one also. Okay? So what is that? This is a pion that is passing through the liquid, and how this so pion is also ionizing the atoms. So this was not only interaction, antiproton interacting with the target proton, but pion is also interacting with the atom, ionizing the hydrogen atom. Then bubbles will be formed because of pions also. Once a while, this electron, outermost orbit electron of the atom, this gets kicked up with a very high momenta. So if it has a very high momenta, it will leave the track. So almost you will be able to see that it has come from the atom which is close to the bubble, and then it will form the trajectory. Okay? And it will, because its mass is very, very small, so because of the low mass, high momenta, it will have the spiral trajectory. Okay? That can tell you even the direction, from which direction the particle is coming. If it's like this one, if something like this comes like this thing, okay, so that will show that this particle is going from this direction to this direction. Okay, that you can find out once a while that what is the direction of the particle by this spiral, direction of the spiral. So this is the bubble chamber experiment, first experiment, where you have anti-proton proton annihilation giving rise to the pions, and pions could be 2 prongs, 4 prong, 6 prong, and 8 prong. Okay. So what you performed in the lab, you just count the particles, how many are entering in the chamber. Some of them are interacting and some of them are just going without interaction. So you'll have this track is going, this is also going, this is almost also going, and only one is interacting over here. Okay. So when you perform the experiment, you look at the reference frame. What are the reference frames? Reference frames is the location where the beam is entering, that's the entry of the chamber. Okay. So at the entry of the chamber, you count how many beam particles has entered. So let us suppose you have 4 particles. So you first count how many particles has entered. So one measurement is counting the number of particles which are parallel. There could be some cosmic ray, there could be other particles. Because all the 4 particles, they have the same momenta, 760 MeV. So if they have the same momenta, their trajectory would be similar. Okay? They will have same curvature. So you'll find out that all the parallel particles, they are the beam particles. You count them, how many beam particles are there, and then count how many are interacting. Okay? So if there is only one interaction, so that means out of 4, only 1 has interacted. And you can find out what is the cross section of this one. You know the total length of the chamber. This is the length of the chamber. You know the density of the liquid. By knowing the density of the liquid, by knowing the length of the chamber, you can find out what is the probability of these interaction of antiproton with the hydrogen. So this first measurement is, you count how many particles are entering, then see how many are interacting out of the so many, and then count how many secondaries are produced. Okay? If it is elastic scattering kind of thing like this one, you note down as a scattered one. This is not a 2 prong, it's elastic scattering because this is not a strong interaction. Okay? Then you count pion like. So difference between this and this one would be, here one would just a scattered proton which has come from the nucleus and length is very, very small. Here this is not a scattered proton, it's a pion. So you have 1 pi plus, 1 pi minus, this is a 2 prong. So you count only these 2 prongs over here. Then you can say 4 prong, 6 prong, and if you are lucky you can get the 8 prong also. Okay, but which you may not get it. So that is and then you plot it, this kind of a distribution that will show the probability of production of each individual particle. So that is the first experiment where you have antiproton interacting with the proton and giving rise to this one. Okay? There is a second part of this experiment. So what we have studied, there is a possibility that you have antiproton interacting the proton and antiproton. This is elastic scattering. There is this possibility also. P bar P, that means P bar is your baryon number is -1, baryon number is +1, so net baryon number is 0. This also baryon number is 0, charge is 0, charge is 0, both are strong interaction. So here this is another possibility, that antiproton interacting with the proton, giving rise antineutron and neutron. Okay? So this antineutron, does it have any charge? So it has no charge. Neutron also doesn't have charge. So how it will look like in the bubble chamber? you have bubbles, and suddenly nothing further, no track further. Okay, so what has happened? Antiproton has entered, it interacts with this atom, ionize it. This is also interaction with the hydrogen atom. This is hydrogen atom, this is also hydrogen atom. Then here, rather than hydrogen atom, here it interacts with the proton in the nucleus. Okay, and charge exchange, this is called the charge exchange takes place. So it is coming from, you have antiproton, this is U bar D, bar. Then you have proton, okay. So interaction, then you will produce, one of them would be going, this becomes your D, and this becomes your neutron, and this will become your N bar. Okay, so this U will become converted to D, and this will become your U. Just look at this one. Okay, so what has happened here? No track, but particle is still going. You cannot say they have stopped. So antiproton interacts with the proton, giving rise to antineutron and neutron. Okay, now this neutron is moving. It doesn't have any charge. It won't ionize. This antineutron is moving, it doesn't have any charge, it won't see any bubble formation, so there will not be any trajectory. But they are moving. Okay? So what is the possibility of this neutron interacting with the proton? It won't be electromagnetic interaction because neutron doesn't have charge. This neutron can interact with a proton. Okay, this won't be electromagnetic interaction, but it can be a strong interaction. And here you'll have neutron interacting with a proton, and it's kind of a scattering. Neutron-proton scattering. If energy of neutron was large, then you can create pions also. So that would be a neutron-proton interacting with the pions also. But here energy is very, very small, so it would be just a scattering, and this proton will get kicked off like this one. The proton will now here proton will have track. So if proton has a track, nothing was visible here. Suddenly you find a small track, and because it's a proton track, it's a scattered one. If it is scattered, momenta is small. If momenta is small, it will go to a very small distance and then stop. Okay? So you'll have very small length track, and that's your proton. So from this direction you can see there could be a neutron coming from here and then interacting with the proton, and proton get kicked off, and then this keeps on moving. And this is your neutron-proton scattering. So you can study the neutron-proton scattering. So this here. So the second, what is the second experiment? Second experiment, what you are doing in this one, N bar P. You have two experiments, no?
Yes, sir.
So the second experiment is your N bar P. This is your N bar, this one. So this one is now moving, and it may interact with a proton. So you will have N bar P interaction. So some of you might be able to see. So what you are having, P bar in the chamber, coming, and here you have the track bubbles, and then no track over here, and bar over here, and now it finds no trajectory, and it interacts with the proton. So it's your n bar p interaction. So now baryon number for n bar is -1 plus 1 over here. Baryon number is 0. That means you don't require in the final state as a baryon. So pions would be created. Charge has to conserve. So only one positive. So you'll have pi 0. Okay. You will see this one would look like a one prong. You can have pi 0, etc. This would be your 3 prong. You can have 3 pi plus, 2 pi minus, and n number of pi 0. That is your 5 prong. Okay. So what is this one is? What type of interaction it is? This is a strongly interacting particle. Target proton is also a strongly interacting particle. A strong interaction takes place. This is antibaryon. This is baryon. Antibaryon, baryon annihilates, give rise to the pions. Okay. So this is 1 prong, this is 3 prong, this is the 5 prong, and all the conservation law of the strong interaction will be applicable over here. And that's how the particles would be. Now how you differentiate between this and that one, antiproton-proton interaction. In this case, you will not find anything over here. You will find only one trajectory over here, and that's positive. You have to always remember what is the direction of magnetic field. That's your clockwise direction or anti-clockwise direction. So one prong would look like this one, no connectivity, nothing here. But mostly students start counting one prong from here. That's not there. Because at this place you are trying to study the antineutron interacting with the proton. You cannot get the beam of antineutron. You could perform a separate experiment, get a beam of antineutron, accelerate it, try to have interaction with the target. Antineutron beam cannot be created. You could have only secondary like this one. You cannot accelerate. So if you cannot accelerate, you cannot give the fixed energy. So in this case, energy is variable. Whatever outcome over here, energy is shared between this neutron and antineutron, that would be the energy of antineutron. Okay? So this antineutron is coming. So rather than beam of now antiproton, what you have a beam of antineutron. That is the beam of antineutron. Interacting with the proton and giving the 1 pi plus. Okay? So this is your one prong, or you will get this like this also. That will look like 3 prongs. So you mostly in the nomenclature what you are writing always, that is stop. You have to first look at in the chamber. First you have to look at where the particle has stopped. It is not really stopped, but it's a charge exchange has occurred. Antiproton has converted into the neutron, and proton has converted into the antineutron, and that is how this charge exchange occurred. Okay? And in this charge exchange, antineutron keeps on moving with a larger momenta as compared to neutron. So antineutron moves and then interacts with the proton, and that annihilation takes place. Antineutron proton annihilation takes place, and you get 1 pi plus, or you can get 3 pi plus pi minus, or you can get 5 pi plus pi minus total. So in the chamber, it will look like there is a gap from the stop. So firstly, you have to look at the stop, then see if downstream is there something. Okay, further downstream is there, you have any tracks over there. It could be 3-prong, it could be 5-prong. But they have to be pointed towards this one. You may not see like this also, that something is coming in this direction. So that means the parent particle is coming from other direction, this direction. That is not the case. In your case, anti-neutron is coming from, it has emerged from here, it has moved in the direction, and then you have seen the 3 prongs, and that these 3 prongs has to be pointing towards the interaction point, like this direction. Okay, so that is your second experiment. So first experiment is your P bar P interacting with the antiproton beam is coming, interacting with the proton, giving you the 2 prongs or 4 prongs or 6 prongs or 8 prongs. In this case, N bar P is coming, interacting with giving the 1 prong, 3 prong or 5 prong events. Okay? So you have to count first how many particles are entering in the chamber, and that you can see only when you have the fixed marks, and beyond the marks how many particles are entering, and all these particles has to be parallel, because this is a beam particle. Beam particles are carrying the exactly same momentum, so curvature would also be the same. Okay, so you count how many of them are there, how many has interacted. So you can have more than one interaction also. Once interaction take place, then you count whether it's a P bar P, okay, and in the P bar P whether it's a 2 prong, 4 prong or 6 prong or 8 prong. In N bar P, you will not get a number of tracks directly at the interaction point. There's a gap between this point and then further down you will find either 1 prong or 3 prong or 5 prong. So one is difficult because you will see one like this one, it has to point over there. Firstly, probability, if you look at this plot, probability is less for 1 prong. Secondly, it is difficult whether this prong is coming directly from here or is some cosmic ray track, or so 1 prong, 3 prong or 5 prong. And then you measure the probability and plot that plot, make the plot of the same way like this also. Almost like this. So this is the number of events and this is the number of prongs. Okay. So bubble chamber is the detector. That's like a nuclear emulsor, almost like a photographic film. So rather than photographic film, you are taking the big bubble chamber, almost as big as this room. This is not a, and then you cool it to a very low temperature and apply it to a very high pressure, and then take the picture from different cameras. So whenever beam is sent, you release the pressure little bit, not really huge. So if you release the pressure too much, then whole liquid will start boiling. Okay? So you release the pressure little bit, and then wherever ionization has taken place, so those points would be condensation points, and at those condensation points there will be bubbles would be formed, and you take the picture of those bubbles. Okay? And that the trajectory of the particle will be shown like a sequence of the bubbles, and that will give the direction of the track. Okay, that will, and if you do the through the computer, you make the 3D picture, then you will be able to see this is the trajectory of the particle. Okay, thank you.